So to the topic at hand, what is it that makes small fields so challenging? And of course, it sounds simple, but the first item on my list is size, because really working with very small fields takes a lot more precision and alignment. It takes a little more care with your choice of detector just to match the size of the field itself. A few other things that I will touch on as I go through this presentation: source occlusion. There are energy changes in your beam as you're collimating down so far to get to these small fields. The shape of the penumbra and the influence of the penumbra on your field becomes more critical at these small fields. The loss of lateral charge particle equilibrium really affects the detectors as well as your knowledge of the dose within those fields. And a lot of the stuff I'll talk about come from a couple very key references, which if you don't have them, I highly recommend getting them. One is the IPEM report 103 on small field megavoltage photon dosimetry. That's this book right here. And the other one is the joint publication from the IAEA and the AAPM regarding small field dosimetry. So that's Technical Report Series 483 or TRS 483. So TRS 43 in particular has a nice definition of what small fields are. And so from TRS 43, small fields have at least one of these three conditions, either and may have more than one. Loss of lateral charge particle equilibrium on the beam axis. They can have partial occlusion or blocking of the primary photon source by the collimating devices that are along the beam on the beam axis. Or the size of the detector is similar to or large compared to the beam dimensions. So if we start with the first item that I had on my list, the physical size of these beams. Usually we're talking somewhere in the order of 4 to 40 millimeters. Of course, if you start entering the microbeam realm, they may be smaller than this, but for general purposes today, we're talking about small fields in that range of 4 to 40 millimeters. When you define your field size for this small field, you have a couple of choices. You can define it based on the setting that you've programmed into, say, your linear accelerator to say, I would like to have a 5 millimeter field. Or you can define it based on something like the full width half max of the field. And as you get down to these really small fields, those two don't necessarily coincide. Because this illustration from the publication by Das et al. is a good illustration for this. Where you're looking at a larger field, you can see that the jaw definition by these vertical lines corresponds quite nicely with full width half max. That's usually how the jaws are defined, the shape of the end of the jaws, in order to get that sort of definition for the majority of your fields. And as you decrease this field size and you tighten up that width between the collimators, now suddenly your edge shape from one jaw overlaps with the curve of the edge shape from the other jaw, and your point of your field is now lower than that plateau was originally. And we talk about output factors decreasing as you get into these smaller fields, but the practical matter here is that because of this decrease in the magnitude of the field shape itself, the profile, this full width half max no longer lines up with the jaw sizes. And as you go to extremely small fields, that effect is greatly magnified. So that's something to keep in mind as you're defining what size field you're measuring. Actually, the full width half max matters a lot more than what you're setting for your jaw collimator settings when it comes to your detector. But when you're talking about source occlusion and those other things that are influenced by the physical position of your collimation system, then it's key to keep tabs on where your jaws are as well. The other point I'd like to make about small fields, because we're working in this very small realm, a slight misalignment of a detector or ultimately of a patient causes a much larger geometric and dosimetric miss or error in the dose that you're trying to deliver to a particular point versus the dose that you actually deliver to that point. So alignment is key, not only for patients, but also for dosimetry measurements. The second point on my list is source occlusion. And these images come straight out of that IPEM report book that I cited at the beginning, where as you have your jaws out for larger fields, this full, usually Gaussian type shape of the source of the beam where the x-rays are being generated within the target, it is seen by a detector here along the central axis. As you collimate inwards, you can see the illustration shows that primary source coming from direct view between your detector and the beam source. But collimating down even further means that you're actually blocking some of the direct source that would come from the edges of, or direct beam that would come from the edges of that source, which can affect both the energy and the output that you would measure at that point. So you get reduced scatter from the primary collimator and from the flattening filter, but the key point here with source occlusion is that you also reduce that direct beam effluence from the source itself. The third point, lateral electronic equilibrium. This does tend to break down as you get to smaller fields. There's less lateral scatter. Sorry, there's a question that just came up. Let me see. I don't usually share my slides, but you will get a link to the video of the presentation. If you have a particular purpose that you want a copy of my slides, contact me directly or contact us through the website, and we'll see if we can make arrangements for that to happen. I don't just put them out in the public realm, but I'm happy to help, especially for educational purposes. Lateral electronic equilibrium, the equilibrium condition is usually easiest to state that your lateral scattering distance has to be equal to or greater than the range of the electrons from your beam. So if I translate this into a kind of practical application terminology, you may start losing your lateral equilibrium when your beam width is less than 2 times your Dmax depth, which means that your higher energy beams, if you look at this plot here, your higher energy beams lose their plateau, lose that lateral scattering equilibrium sooner as you're going down into smaller and smaller fields than your lower energy beams do. So your detector positioning, any beam perturbations, all due to the makeup of your detector, that sort of thing all come into play sooner for the higher energy beams than they do for the lower energy beams. This also kind of brings home the point that it's very important to characterize not only the output at the center of your field, but your profiles as well, because they will be very different between a 2 centimeter or 1 centimeter beam for higher energies than it is for a 1 centimeter beam for your 6NV or a cobalt beam. All right, so getting past the beam quality problems or the impact of the fact that we're looking at small beams, the detectors themselves also impact our measurements. So the next things on our list really talk about the detector that you're choosing and how that affects your measurement as we get down into small fields. So the first thing to think about as you're selecting detectors is how big is my detector and what is it shaped like. So if you're talking about physical size of the detector, you need to look at not only, what is the radius, what's the volume of my chamber, that sort of thing, but we like to talk about chamber spot size. And if you have a spherical spot size, then that means that the area that impacts your measurement is equal in both directions, along the direction of the chamber and perpendicular to the direction of the chamber. If you have a chamber that's stretched out a little bit more, you need to be aware of your orientation within the field as well as this longer axis of your measurement, because that impacts the volume averaging that you may have over these highly peaked and non-flat beams. So if you're trying to determine beam penumbras very accurately, it's very critical, again, to think about how big your detector is, especially in the direction of the scanning motion, but also relative to the overall field. Consistent and accurate positioning of your detector is extremely important in these situations. Having a water tank where you can potentially scan to find the maximum output in both directions, or in multiple directions, in order to be sure that you really are lined up with the center of the beam, is quite helpful. If you're looking at film measurements, film is a really useful tool for getting the overall shape of the field, particularly looking at the penumbra, how steep that fall off is. But it is good to be aware that when you get down to extremely small fields, and I'm talking the 5 millimeter type pinpoint field measurement on your film, the way film scanners work, sometimes you can get additional light scatter around the edges of those very small points. And that can decrease the measured value in the center, because your film scanner doesn't recognize just how dark the film is at the center if it has that extra light scattering around. So just to be aware, as you get down to these really small fields, your film scanner may artificially flatten them just a little bit, but a little bit, due to some of the scatter within the film scanner itself. So having multiple detector types, having multiple different ways to measure your field profile, not just relying on one type of detector, is critical here as well. The plot that I have on the right-hand side here came from a publication from Meltzner and DeWord about gamma knife fields. And what they were looking at was not only the size of the detector, so the active area of the detector, the air volume, if you will, is defined by these solid lines. And you can see, if you're looking just at the size of your detector, the smallest helmet, the 4 millimeter helmet on that particular gamma knife model, had some volume averaging within the, well, it's always volume averaging, but had some profile changes within that detector region that affect the volume averaging calculation. But they were also seeing decreased measurement values in the 8 millimeter helmet, which should have been flat across the active air region. But what was realized in the analysis of this study was that because of this lateral scatter change due to the air volume, they actually needed to consider the buildup on either side of the detector. So the full size of lateral scatter equilibrium affected the measurement, and they saw decreased values for that 8 millimeter helmet compared to a TLD measurement, for instance, because they had to consider this scattering area next to the air volume, not just the volume of the air itself. So again, something to keep in mind as you're calculating your volume averaging or looking at your output factors, that air volume is not, the active volume of the chamber is not the only thing to be considering when you're looking at the impact of the detector on the profile. Perturbation of the beam, as with that air volume, decreasing the scatter right there where you're taking the measurement. If it really depends what type of detector you're putting in the beam. If you're putting in something like a diode that has a higher density, you're going to change the interactions right there at your point of measurement. If you're putting in an ion chamber that has a lower density, you change the interactions there again. So you are perturbing the fluence right there at the point of measurement with whatever type of detector you have. So the questions to ask yourself as you're choosing some of these detectors is, with my ion chamber, how big is the air cavity? How much am I decreasing that scatter relative to the full size of my beam? Is that affecting the measurement itself, because I'm no longer getting the lateral scatter out from where that water is being displaced by my air cavity? And for a diode, what's the density of the diode? Some diodes are considered compensated diodes, which means that they have usually a lower density region right next to the higher density diode in order to try and balance the interaction and decrease perturbation that way. Those work fairly well at the energies they're designed for, but sometimes they're not ideal across the board. So you have to be aware, if you have a compensated diode, what was that designed for, and is that going to cause different sorts of perturbations at the other energies or other field sizes where I'm taking it outside the range that it was designed for. There are often published corrections available for some of these detectors. This is an example from a publication by Paolo Francescon and et al. That shows both the increase or greater than unity correction needed for the chambers that have low density and the less than unity correction needed for detectors that have higher densities. If you're using these published corrections, which is great to do, it's good to have these references, make sure that you're not deviating terribly far from the published conditions, because where they're really calculating these perturbations, where they're calculating these correction factors, is most accurate right there at the same sort of conditions, the same conditions that they calculated or measured those factors for. Another couple of examples of correction factor tables from, I think this is a different publication from Francescon, but you can see, again, some of the standard imaging detectors. This is the scintillation detector here near unity, but we've got some diodes in this plot, including the standard imaging X-ray D1V here on the green squares. Same thing for some of the I guess this was earlier, micro ionization chambers, again, needing that greater than unity correction because of the low density of the air within the chamber. The third way that your detector can affect the measurements you're making in small fields is the signal level. With an ionization chamber in particular, your signal is proportional to that active air collecting volume, as well as your dose rate, your beam strength, that sort of thing. So your signal to noise ratio becomes more of a concern as your signal decreases. And with these small signals, you need to be certain that you have an appropriately sensitive electrometer, preferably one with a low range that's been calibrated, right? So that you know that the values that you're getting at those low currents are valid. A diode is nice because it gives a larger signal than you get from microionization chambers. But it has, of course, trade-offs with the density and lack of calibration link to the national standards labs. Consider your signal to noise ratio. I know I brought that up under the signal bullet up above, but in terms of your signal to noise ratio, you need to be sure that you have proper warm-up for your electrometer. All of those electronic components, the resistance changes slightly, that sort of thing, as they come up to temperature once they're on, once the bias is on, that sort of thing. So check your leakage, make sure that your system is stable, make sure you give your electrometer a sufficient warm-up. Match the signal strength that you're measuring with your detector with the appropriate electrometer range. And then the one that was new to me a few years ago, I learned from one of our engineers in-house, is that the triaxial cable you're using itself, when you're looking at these extremely small signals from small chambers, if you have a really long triax cable that was wound tightly around a spool or something like that and gets unwound for your measurements, that cable can produce electric currents called triboelectric effects for up to several hours after it's been unwound, as the physical strain on the cable relaxes. So if you zero your especially if you've just unwound your cable, but if your electrometer doesn't hold at zero and you keep having to re-zero because it's drifting, you may actually have a cable problem and not an electrometer problem. You also need to be a little careful, of course, with small fields. You're not usually putting cable in the beam because you're trying to radiate just your tiny detector, but there can be cable-induced signal due to irradiation as well that can contribute to your signal to noise. What about the accuracy of your measurements? If in terms of the detector itself, some detectors have energy dependence that needs to be considered, not just for the nominal energy of your beam, but because as you are blocking that primary fluence, you get that source occlusion as you are moving into regions of pure scatter, really. Energy dependence shows up a little more quickly. So some diodes can actually have a low response out of field where they underestimate the dose due to just that low energy scatter, which if you use that for your treatment planning can lead to underestimation of the larger region of low dose in your stereotactic patients. I mentioned compensated diodes. Again, that could be good or bad depending on what field you're measuring, but they can have a little bit more energy dependence as well. Energy dependence also shows up in depth dose curves. So your corrections may end up being depth dependent if you have a strongly energy dependent detector. And of course, scatter conditions can affect that, can change that response if you have a detector that is highly sensitive to changes in the low energy spectrum. Angular dependence is something you should also be aware of. Some detectors have a very strong angular dependence, and I recommend using detectors in the orientations that they were designed for. It's tempting sometimes to turn them a different way in order to get what looks like better resolution in terms of the cross section of the detector, but you may actually be opening up a lot more problems by doing that than by using it in the orientation for which it was designed. There can also be dose rate or dose per pulse dependencies for your detectors, and this requires understanding both your irradiator or your accelerator and your detector. So if your accelerator increases the dose rate by just increasing the pulse repetition frequency, then your dose per pulse dependence doesn't show up within that particular measurement. But if you are on that machine, but if your machine changes the dose rate by increasing the dose per pulse, then you need to be aware of dose per pulse dependencies with your detectors. And anybody moving into the flash realm, dose per pulse becomes a big issue. So we can talk about that later too. That's always fun. Other detectors, other issues, I should say, other ways detectors impact your measurements. Leakage from your detector, drifting of detectors, or degradation of detectors with radiation damage. How repeatable is your detector? What's the actual resolution of the measurements? Can your detector be calibrated? All of these factors can impact how well you can perform the task that you're trying to perform with this detector within small fields. So in the end, that's a lot of stuff about small fields. That's a lot of problems that you have to deal with. That's a lot of concerns you have to kind of sort through. But what are you actually supposed to do in the end? What's the practical advice that we can offer you here? And the options that I would say is that we at Standard Imaging in particular have three very nice options for you in terms of megavoltage beams first. I have some other energy stuff later, but for megavoltage beams, we have some established technology. There's, of course, known perturbation issues with diodes, but we have the X-rated D1H and D1V diodes that are great for small fields. There's the new technology in terms of the plastic scintillation detectors. And I say new, but the W1 has actually been out for 10 years now. So I probably need to change that and not call it new technology. But it's unfamiliar to a lot of people. We're used to working with ion chambers. We're used to working with diodes. Not everybody has had experience in the optical realm. So we'll still call it new technology for now. Maybe I'll consider changing that the next time I give a talk like this. And then the third option we have for you is that old standard, the ionization chamber, which is finally working properly in miniature form. There are a lot of issues with microionization chambers and polarity effects and that sort of thing, just because it's so hard to build a chamber in this small size. But the X-rated A26 microionization chamber has been proven to be a wonderful option for these small fields. And I'll explain why. But what I do recommend, every detector that you're looking at, including our detectors, has both strengths and limitations. And so the best solution that you can have for your small field measurements really is a good combination of detectors and detector types. So that you can have good confidence that you're making the corrections properly, you're really evaluating your measurements properly, because coming from both sides of the problem for your measurements line up and your answers line up. So in terms of our diodes, the D1V and the D1H are the same physical diode, they're just in two different shaped housings. So this vertical one is designed for scanning so that you're not perturbing the water around the point of measurement. The other one is designed for a little bit more ease of use in slab phantoms, so that this could be in a milled out slot in a slab phantom to be able to do some closer to surface type measurements. They're unshielded diodes. They have a 1 millimeter diameter active region spot size, and there are some publications with correction factors for the D1V and the D1H. Strengths of these diodes, as I mentioned, diodes are well-established technology. We have been using them for years. You can use them for scanning very easily. That 1 millimeter active area gives you minimal volume averaging. Our diodes have a low angular dependence, so you don't have to worry about the angle when you're scanning off to one side. Although with small fields, that's of course less of a concern than a larger field. Limitations of these diodes, not unique to our diodes, but limitations that should be known, is that the diodes are not water equivalent. So you do require corrections for the impact of the higher density diode compared to the water. And there is some angular dependence. They are not perfect. You can't just go shoot them from the side and expect it to be exactly equivalent to what you would get straight on. But they are great for scanning or for some of those phantom measurements. Our scintillation detectors are what I still like to call new technology, unfamiliar technology to a lot of people, although scintillators have been used for decades. Ours are an organic scintillating material, BCF12, that is coupled to a PMMA optical fiber. The active region, depending which of the scintillators you're talking about, is either 1 millimeter diameter, 1 millimeter long, or 1 millimeter diameter and 3 millimeters long. So what we call the W1 is the 1x3. The W2 has dedicated electronics and a user replaceable fiber, and you can have either the 1x1 or the 1x3. The major advantage of these scintillators is that they are water equivalent at megavoltage beams, photon and electron. The difficulty with these and why there was not a commercial product for until ours came out 10 years ago is that you have to account for the Cherenkov, sorry, I learned the proper pronunciation from a Russian last week, from the Cherenkov effect. So Cherenkov light is light that's produced by electrons moving faster than the speed of light in that particular medium. So the standard description is that it's the shock wave in the light world similar to the sonic boom that's generated when a jet travels faster than the speed of sound. It creates this blue glow that you see in the classic picture of the reactor coolant pool, but it's produced within that optical transfer fiber. And so depending how much fiber is in the beam, you would have more or less of this contaminating Cherenkov light. The other aspect of the scintillators is that because they're a plastic, they do degrade with dose, and so the signal decreases slightly over time as it's used. So you can cross-calibrate it with a detector that you have, and then periodically recalibrate it as the material accumulates dose in order to keep your measurements accurate. in order to use, or the system that we use to account for the Cherenkov light is a 2-channel chromatic correction. And I apologize, I thought I had put the reference up here. I will have to put, I'll have to put that in the chat at the end. I'm blanking on the name right now, but there's a published paper, and we can follow up with that if you want, on the 2-channel chromatic correction, where our scintillator is a blue scintillator. And the Cherenkov light is a broad spectrum contaminant. So for our, when we take in the signal from the scintillator and the optical fiber, we split the signal into a blue portion of the spectrum and a green portion of the spectrum. And before you take measurements with your W1 or your W2, you would do a set of characterization measurements in which you would keep the dose to the tip of the scintillator constant and change the amount of optical fiber irradiated, so that you have 2 sets of measurements with identical dose to the tip of the fiber, but only the Cherenkov contribution is changing to the measurement. From those 2 sets of measurements, we can calculate what we call a Cherenkov light ratio. So this is the difference in the blue signal between the maximum fiber, the large amount of fiber in the field, and minimum fiber configuration, where you have small amount of fiber in the field, divided by that same difference for the green channel. And from this, we get a correction factor that can be used. Multiply the CLR times the green channel measurement, and you subtract that from this blue channel measurement with your subsequent measurements, which gives you back just the scintillation signal. This is built into our Supermax Supermax electrometer for use with the W1 scintillator. It's just the scintillator and the optical system for collecting that light. So it does require the 2-channel electrometer in order to gather this blue channel signal and green channel signal separately. The W2 has a dedicated electrometer, which has both the optical signal collection portion as well as the signal processing electronics to do the 2-channel measurement and the Cherenkov correction automatically. If you want to do a dose calibration for your scintillator, you give it a known dose and a reference field size, and that just becomes a constant multiplicative factor to do that unit conversion, really, between the scintillation signal, corrected scintillation signal, I should say, and the dose. We provide a couple of different configurations for doing these characterization measurements. There's a little 3D printed jig that can work in a water tank in order to do this in a smaller field. It fits in a 10 by 10, or if you have a smaller field, you can kind of center that over here on the tip of the scintillator. It has a way to have your minimum fiber configuration with the fiber coming straight out, and the larger amount of fiber in the field by wrapping it around here. The virtual water slabs that you can also that we also provide for use in slab phantom configuration have the same sort of thing. It's a channel milled out straight out for the minimum fiber configuration, and one wrapped around the edge here in order to have more fiber in the field for that maximum fiber configuration. So the W1, as I mentioned, has that 1 by 3 active scintillation region. And what's really cool about this one is that it's actually listed in that AAPM and IAEA TRS 483 small field publication with a KQ perturbation factor of unity for every field size, every table that it's in. It's a wonderful confirmation of the water equivalence of this detector. I will point out that some of the detectors don't have data shown for the really small fields, and that's really because either the uncertainty or the stability of the detector at that level was not sufficient for it to be included in the publication. So if you're looking for missing data, that's why it's missing there. With the W1, that really the strengths of this detector are that it has that beam quality correction factor of unity. So you don't have to be concerned with the change in energy spectrum as you're going to these small fields or as you're going to deeper depths. That's really the confirmation that it is water equivalent for MV photons and electrons. We have not seen dose rate or energy dependence with this for standard megavoltage therapy beams. There is a negligible temperature dependence. I think, oh goodness, I haven't had to say this in a while. It's about 0.1% per degree Celsius. I can look that up if you have a concern. Generally speaking, if you're doing all of your measurements at room temperature, you don't have to worry about accounting for temperature. If someday we do license this for on-skin type patient-specific QA measurements or monitoring measurements, then you might have to start applying a temperature correction between the body temperature or skin temperature and your room temperature at which you calibrated it. Limitations of the W1 is that this was really designed to be a point detector, an output factor type detector. It was not designed for scanning. It's a small field detector too. It's not really designed for large fields. If you have a really large field, you'll have a whole lot of more Cherenkov compared to your simulation level, and so that correction uncertainty becomes higher. It does have a very low signal to noise ratio, so you need a highly accurate low channel signal electrometer. That's why we use our Supermax for that one. You also get higher uncertainty out of the field in the low dose region. The tails of your profiles are maybe going to be a little bit high with the W1. I think there was a poster from Malcolm McEwen a number of years ago covering that particular topic. And it's really because you're bumping up against the noise floor of your electronics. You can't measure that low signal with as much accuracy as you need for those out of field measurements. So this is a good in-field output factor type detector. It's not the best for scanning. As I described for simulators, it's not a device that you can send in for calibration. You have to give it a cross calibration with a reference dose and an occasional recalibration as the plastics degrade with dose. The other limitation is that there's a bit of a learning curve to this, just because optical signal measurements are not intuitive to some users. And so troubleshooting why my measurement doesn't match what I think it maybe should be becomes more simple as you get used to the detector, as you get used to using an optical fiber and handling an optical fiber and interpreting data from that. But it is a little bit of a learning curve if all you've ever used is ion chambers and diodes. With the W2, this was our second generation device. We were able to improve the optics in order to allow a decrease in the active region of the scintillator without compromising on signal to noise. So we were able to go down to a 1x1 millimeter scintillator. We also have, we provide it with a 1x3 as well, because there are so many W1 publications, including TRS 483, that refer to the output and the response of the W1. That provided a nice link for some people back to those W1 publications. It also gives you 3 times the signal. So your signal to noise as you're in the mid-range of those small fields rather than the teeny tiniest ones is nice from the larger field. I just noticed there are questions coming in that I forgot to answer. So I'll talk about the scintillator ones here momentarily, and then I'll circle back, sorry, to the chamber questions. My apologies. So for small fields with the W1, if you're mounting it vertically, that's the question. Is there an advantage to mounting it vertically? Let me go back up here. Actually, no. So that was tried quite a bit in order to try and get that 1 millimeter cross section. The problem with mounting this scintillator vertically is that you are, first of all, putting more fiber in the field to get more Cherenkov, which under normal circumstances is fine because we can correct for that with the CLR factor. But the spectrum changes slightly because Cherenkov is actually preferentially produced at an angle of 45 degrees to the direction of travel of the electrons. So not only are you generating more Cherenkov within your optical fiber, but you're generating it at an angle that is, we're relying on total internal reflection down this optical fiber in order to collect the signal. You are collecting and channeling more of the Cherenkov signal than you are when the detector is perpendicular to the beam. And so the curve, where exactly that curve in the fiber happens, can impact your spectrum just slightly, can impact your uncertainty, and then ultimately impact your measurement. So we do recommend that you use the scintillators perpendicular to the beam and not turn them end on. You can, it just adds some uncertainty to your measurement. The question of, is the Cherenkov contribution dependent on field size and beam quality? It's dependent on the field size. I should say that the amount of Cherenkov that you get depends on the field size, because that determines how much of your fiber you're irradiating. But the paper that I need to pull up so that I can give you the reference, that defined this two-channel correction method. Sorry, pull up my files over here while I'm talking. Investigated this, and really the spectrum of the Cherenkov doesn't change, just the amount does. And so as long as that spectrum doesn't change, that CLR correction factor remains accurate for a range of amounts of fiber in the field. So it's not a correction that is field size dependent, but if the Cherenkov spectrum actually were to change, that's when you would get a change in the correction factor, or need to change the correction factor. Let's see, I think there was another question here. Zach, I'm not sure what you mean by how is the optic cable able to fit in the small field sizes. Maybe a better, I'll try and give an answer, and if it's not answering your question, type your question again and I'll try again. For very small fields, you would have, let me go back to this, for very small fields, you would have very little optical fiber in the field, and so this Cherenkov light, this curve would be very low. And so therefore your green signal is going to be quite low, which means that your CLR times your green signal would also be low, and therefore you're subtracting only that small amount from the blue channel. Oh, good, thanks. I'm glad I answered your question. So it does work. It does work well down to those small fields, even where you're reaching the point where you're not generating Cherenkov much. Okay, so the W2 then, having those dedicated electronics, we were able to decrease the electronic noise floor for this as well, because we're not dealing with a lot of long triaxial cables, and we're doing all of the signal processing with circuits that are designed for these very small signals. And so that combined with the optics advancements helped us to be able to go to that 1x1 field size. The other advantage of the W2 and its electrometer is called the Max SD for simulation dosimetry. The Max SD can do that Cherenkov correction every 10 millisecond integration, and then convert that digital signal back into a corresponding analog output that is linked to your Cherenkov corrected measurement, and output that as a current that can be read in by your 3D or 1D water tank scanning system. So you can use the Max SD, then becomes, actually I think I have pictures on the next slide, becomes this pass-through where you would put your scintillation detector. So here's a W2 fiber. We have a stem adapter that allows this to be held in a standard chamber holder within your water tank without crushing that optical fiber, and allowing you to get a little distance from your scanning apparatus. That fiber then goes into the Max SD, which you've already previously calibrated or set up your CLR, or you can do it before you start scanning via its interface. It can then just operate in pass-through mode, where it gets the signal from the optical fiber, does the Cherenkov correction, and then outputs that proportional analog signal, the current, to your water tank scanning electrometer, like our DOSView 3D electrometer that's shown here. From the point of the water tank system, this detector looks like a diode, by which I mean you're not applying bias to it, but when the beam is turned on, a signal is received by your electrometer. The advantage of this really is you can scan to find the center of the field. You can collect profiles, you can collect PDDs. If your system will let you do, well, you could drive it to depth and get point doses via the MaxSD itself, which would be the most accurate way to do it, rather than adding in the additional electronic noise from your scanning tank electrometer if you're doing point dose measurements that way. But it's really a wonderful tool for scanning small fields. The disadvantage is, again, because it's a small signal device, you do have to scan slowly. So we do recommend that you make measurements at about 1 second per dwell point in order to get low noise, high accurate, but low noise measurements. There's a question from Luke: how sensitive is the technique and setup for the CLR measurements? Not terribly sensitive. It's fairly forgiving. You do want to repeat it semi-regularly, especially if you're using the device a lot, because what happens as the fiber ages is that clear PMMA fiber starts turning yellow where it's received a lot of radiation dose. I'm sure a lot of you have seen the old PMMA phantoms on the shelf at the clinic or at the lab, and they're really yellow. And that's what happens within this fiber as well. And that change in color of the fiber does two things. It attenuates some of the signal that's passing down the fiber, but it also changes the spectrum just slightly because it's a color filtration. And so that's why you have to redo both your CLR measurements in order to get that balance between the blue and green accurate as your fiber's degrading, but also your dose calibration, because the signal itself also decreases. So what we've seen, what's published for this, really is about a 2% decrease per 1,000 gray that the fiber receives. Good questions. Thank you for that. Strengths of the W2 really are exactly the same as the W1. It's the same fiber, it's the same analysis method. It just happens to be that we've got those dedicated electronics for it. So we still have that KQ of 1. We still have no dose rate or energy dependence. We still have that same teeny tiny little bit of temperature dependence, so you can ignore it for QA measurements. What we've done with the W2, though, is removed a couple of the limitations that we had with the W1. This is designed for scanning, and it has a better signal to noise ratio, so that out of field measurement to get the tails of your penumbra is much more accurate with the W2. In terms of microionization chambers, we've had the X-Radon A26 for a little while now, and it has been extremely well received in the field. So this chamber was designed as a result of Jessica Miller's PhD thesis investigation at the UW-Madison, working with the radiation calibration lab there. And she was looking at the spurious behavior, the strange behavior of microionization chambers that existed at the time. Where they would show a wildly different response when you change the polarity of the detector. And there's one example over here on the right of what the A26 looks like on this the chamber response versus voltage plot. And you've got the positive and negative bias is overlaying, as you would expect, or as you would hope it to be, where with and every other microchamber, I should say, had strange behavior where one polarity would be something like this red line and the other polarity would be way down here. That was tracked to, whoops, let's see, do I have that? That was tracked to really mismatches in the conductance of various portions within the chamber itself, and a change in polarity of the ionization chamber would cause a shift in the electric field lines due to the change in, or the differences in in conductance between mismatched materials in particular, where the A26 now is made completely of the same conducting plastic, C552 conducting plastic, and so that's why its behavior is improved compared to some of these other detectors. So we designed it to provide to meet these requirements of reference class chambers, because we saw that there was this drastic need, and through that research project that Dr. Miller had performed, we had a good in for how to make that. So as we were designing the A26 in the end, the couple of the things that we were considering is the spot size of the chamber. We tried to make sure that it was, number one, as small as we could make it, in order to make it out of these conducting plastics and have all that nice match of the conductance, but also have it be spherical, so that the orientation within the field didn't matter. We modeled the electric fields to make sure we verified the shape. In terms of volume, our A16 is our smallest microionization chamber, and it has a wire as the central electrode. So the machining values for that are a little bit different, but we're able to make that volume a little bit smaller. But if you look, the spot size of the A16 compared to the A26, although the volume is doubled for the A26, the spot size is only 0.8 of a millimeter larger. So really it goes down to the same sort of small fields that even our smallest microchamber can measure, without having the polarity problems of those other microchambers, including the A26. We also looked at what's the signal magnitude, will the signal to noise ratio be sufficient for the intended use, and definitely, I mean, even compared to the A16, you've got twice the signal because you've got twice the volume. So that helps a lot in terms of measurement stability and reproducibility. Strengths of the A26 then, as I mentioned, a whole lot of all of these detectors really have strengths and limitations. The A26 was designed to be that reference class type ion chamber, to have a spot size that was independent of orientation, a nice spherical spot size. And ion chambers really are familiar technology for physicists. We're comfortable working with ion chambers. We kind of understand where they can go wrong, and how to interpret the measurements. So it's a comfortable space to work in. Limitations of ion chambers, all ion chambers, especially small fields, is that it requires a correction to account for that low density of the air volume in the field. So that was megavoltage beams. We do have a solution as well for small kilovoltage X-ray fields, and that's the X-ray and A20. This is actually a parallel plate chamber that is oriented in line with the stem of this chamber. So you would have your field coming from this side, the parallel plates are oriented this way, and then the stem behind it. So this was designed for things like electronic brachytherapy sources, and superficial skin therapy, that sort of thing. It has just under 2 millimeter collector diameter, so it has very good resolution for these small fields as well, and a very excellent low energy response from 20 kV all the way up to cobalt here. A very good low energy response. I would be remiss if I didn't talk about electrometers. I know I've brought them up a bit. The two that we offer are the Max 4000 Plus, which is a very robust single channel reference class electrometer. The Super Max is the one that has the dual channels that you need if you have a W1 scintillator, and the touchscreen, faster warm up. In terms of specifications, the Supermax does a little bit better with the low range signal, but they both do excellently well in terms of long-term stability, lifetime calibratability, and ease of use. They also have an industry-leading 5-year warranty, which is, I like to say, it's an indication of how confident we are in the longevity of our products, that by default we stand behind them for 5 years. So Thank you so much for your attention. I know I've used up almost an entire hour and I talked quickly and I apologize if I've skipped some questions. I'll circle back to those now. We will be sending a link to the talk if you want to go back and I don't know, share it with your residents, see if they can follow me. Feel free to contact me as well. My email is here at the bottom. I'm happy to follow up with anybody if you have questions. Thanks so much for your attention. I will circle back into my question list and make sure that I have gone through these, but I understand if people have to leave. Let's see. Practical techniques for positioning the chamber at the beam center. So what I tend to do when I'm scanning with, and our 3D water tank does a very good job with this. I know there are some issues with some of our competitors' water tanks, but what I like to do is align as best I can based on the centroid of the chamber. We have some alignment caps that you can use in order to get things aligned. But then once I have it as close as I can with my physical setup that way, I use a fine center for the left perpendicular to the chamber axis and parallel to the chamber axis to make sure that I'm really centered in my field. I think some systems do the fine center from you lose your manual setup. They do it from their default fine center location each time, so it's not a fine tuning. That'd be something to follow up with your tank vendor on. But with our tank, it takes your zero position that you have set, and it'll do that fine center, and then it'll say, I see that you're offset by 0.2 of a millimeter in Y and 0.3 of a millimeter in X. Do you want to make these shifts? And you can make the shift. So that's to me the easiest way to set it up. In terms of the scintillator setup, we don't have an alignment cap for that we provide. The easiest way really to align that is to align your crosshairs to the end of the scintillator and then step it forward within your tank. If your tank is one that will allow this, step it forward the 1.3 or 2.3 millimeters in order to be centered on your detector. But you can also, again, do a fine center with that in order to fine tune it. As long as your water tank allows it. In terms of reference chambers, there's a question on reference chambers. If you're scanning with the scintillator, because you're scanning slowly, you usually don't need to have a reference detector because if you're doing 1 second measurements at each of the dwell points, 1 or 2 pulses one way or the other is not a huge contribution to the overall signal. And so having that reference detector in order to track the pulses measured from the accelerator is not so critical. We do have some larger spherical chambers that can be used with some water tanks. It's some of the water tank electrometers have an issue with the capacitance of the larger chambers. They can be used as out of field detectors. You can also use a diode near the edge of the field or near the water in order to pick up scatter signal that way if you need a reference detector in or for those very small fields. Let's see. What other questions do I have here? Is the W2 also suitable for relative output measurements for the entire range of accelerator field sizes, small and large fields? You know, I actually noticed that in my crossed out lines there. It's still a small field detector. You can use it potentially in, I would say, I probably wouldn't go up above 20 centimeter field. Maybe 15 is a safer limit. It can be, it has been, but your CLR value becomes a little bit less accurate in those large fields when you have a fiber that's starting to age, because the overall balance of Cherenkov spectrum from the proximal end of your fiber that doesn't have as much dose, that's a little clearer, may be a different spectrum than what you're getting from the distal end where it's been irradiated a lot. the question of, do we offer SRS commissioning service for a fee? We have contracted with other groups to do that, but at Standard Imaging, personally, I don't do that, but we do have an organization we work with that can certainly help you. Very knowledgeable, very helpful, so please reach out and we can certainly talk about that. I think I've reached the end of the questions. We've also passed the end of our hour, or maybe we're spot on. Hey, look at that. My other clock is a minute ahead. Thank you once again for your attention, for your engagement, for showing up for this talk. I hope you found something helpful here, even if it's just a review. Sometimes I know a review can be useful to bring some of these issues back up to the front so that you can be cognizant of them as you're making your measurements. And we'd love to hear from you. We'd love your feedback. If there are other topics you'd like us to try and cover in the future, or things that you want to help us improve on, that's great too. We'd love to hear from you. So thanks so much for your time.